And then we can have a look at this task 21, as said about star delta transformation or transform. And the task, the idea is to calculate the equivalent resistance of this circuit between these terminals or nodes A and B. And we have probably already discussed it a couple of times, but what is the issue with the circuit? It's the resistor R5 in the center. Because of this resistor, if we would not have this resistor, then these two would be in series, these two would be in series, these two branches would be in parallel, everything would be quite simple. If there would be a short circuit instead of this resistor R5, if these two nodes here, let's call them maybe C and D, if they would be connected with each other, then these two would be in parallel, these two would be in parallel, this would be in series, everything would be also simple. But because of this resistor, they are not in series, they are not in series, they are not in parallel, they are not in parallel, and everything gets complicated. And so now, how could, in subtask A, how could a delta star transformation help us in still solving this issue and calculating the equivalent resistance of the circuit?
We've got two deltas, so we can transform either the first part or the second part to a star.
Yeah, and so we don't really see the delta maybe yet, but there is a delta connection between these nodes A, C, and D, for example. These are three resistors that form a triangle, not drawn as a triangle, but it is a triangle or it is a delta, and we would have another delta here. So BCD is also a delta. Of course, we do not need to transform both of them, just one. So maybe, maybe let's select, let's say this as a delta, and transform this into a star. So in this case, I will redraw the circuit then. So we still here on this side, we still have node A. And then we have one of the resistors. So then we have a new point that is not in this circuit. And then we have another resistor going to node C. And then we have another resistor going to node D. And let's call this here maybe 0 because it's the star point in the star. And then we still have the remaining resistors R2 and R4. And they then are somehow connected at the end to this node B. Okay, and then we have three new resistors that I will call RA0, RC0, and RD0. And now the question is, okay, how can we calculate RA0, RC0, and RD0? And if we have them, how can we calculate from them the final equivalent resistance RAB?
Well, first it helps to imagine the delta still on top and then the adjacent resistors as a product divided by the sum of all resistors is...
yeah, so at the end, we need to have these formulas. We can check the lecture material, which is somewhere here, which should be somewhere here, and it was this chapter 2. So I will open up the slides. There is here, it's inside this two-pole theory. And so now we do conversion from a delta to a star. This is the derivation, and these are the final formulas. So, as mentioned, each resistor of the star we get from the product of the two resistors that are connected to this node divided by the sum of all the three resistors inside this delta. And of course, we could also check the Wikipedia for star delta transformation and go to the English Wikipedia and hopefully find something there. And then here it's called slightly different, but still the same thing. And so here we have the delta, here we have the star. And yeah, so now you need to check the notation inside the star. They are labeled as 1, 2, and 3, the resistors, in here A, B, C. And so we need to have this formula where we from the RABC calculate R1, 2, 3. And so R1 is the resistor here that is connected to node 1. And at node 1 we have resistors B and C connected. So it's the same thing here that the two resistors connected to this node divided by the sum of all the three resistors. Do I remember this? No. I also always need to check it up. Okay, so R10, the resistor connected to this node A, we then get from R1 times R3, because these are the two resistors here connected to this node, and then divided by R1 plus R3 plus R5. And so here we have at node C these two resistors connected, R1 and R5, and we still divide by R1 plus R3 plus R5. And at the last node, and maybe I should have left more space here, but okay, at D we have 3 and 5 connected, and we have the same denominator of R1 plus R3 plus R5. Okay, next step. We insert values and we calculate the stuff, and luckily all these resistors have very simple values. I just need to set in all these values, and I will, to save some space, directly in my mind cross cancel an ohm. So here we have 1 times 3, let's directly calculate it. We have 3 ohm divided by, and 1 plus 3 is 4 plus 5 is 9.
It's 3 ohm square, no?
Yeah, and it would be 3 ohm square divided by 9 ohm.
Okay.
And so I've directly cancelled one. But okay, let's maybe write it like this, it's more understandable. Okay, so here I have 1 times 5 is 5 ohm square, and we still divide by 9 ohm, and here it's 3 times 5 is 15 ohm square, still divide by 9 ohm. Okay, and so then we can just calculate the stuff, and yeah, 3 divided by 9 is 1/3 ohm. 5 divided by 9, I will just leave it like this, and 15 divided by 9 we can divide by 3, so it's 5/3 ohm. Okay, so now we know these equivalent resistances or the corresponding resistances in the star circuit, and usually in the star circuit, they are smaller. We will see later on, because here it's if you calculate the equivalent resistance, or the let's say the clamping resistance between two nodes here, let's say between A and C, then it's always something that you have here this branch in parallel to the other two, so you connect something in parallel, and that's why here at the end these resistors where you have something in series, they must be smaller so that you get the same resistance at the end. Okay. Yeah, so how to continue?
RCO plus R3.
Yeah, so here we should have RA0 as this resistance, and then we have these two in series, and these two branches in parallel. So plus RC0 plus, this was here R2, this was R4 plus R2, and this is in parallel to RD0 plus R4. Okay, so now we can insert the values, and we have 1/3 ohm plus, yeah, so here we have 5/9 plus 2. So 2 is 18/9, and 18 plus 5 is 23. And this
9.
yeah, over 9 ohm, and this is in parallel to yeah, so we have 5/3 plus 4. 4 is 12/3. 12 plus 5 is 17/3 ohm. Okay, and yeah, so now probably the difficult step here is to calculate this parallel connection. Because these are fractions, of course, we could do something like 9/23 plus 3/17. But 23 is a prime number. 17 is a prime number, so I think at the end it's probably, at least at this time of the day, to be honest, I cannot do such calculations in my head. So let's write a short function in Octave that does calculation of parallel resistors for us. So we take the product divided by the sum. And now we can use this to calculate the parallel connection of 23 divided by 9 and 17 divided by 3. And why does it not work?
70 divided.
There is a comma. So, okay. And so we get 1.7 something. And then we calculate this plus 1/3. And so we get 2.09 something. 2.0946 ohm. And of course you could do this in a mathematical more exact way, but okay, we are not mathematicians, we are engineers. We are totally fine with the solution that we get there.